Hi again. This is part 2 for alkene nomenclature, in particular E and Z. Part 1, if you are first learning alkene nomenclature, part 1 was 03D20. I didn't label it as part 1 when I made the video because I didn't know I was going to run out of time, but I did have a lot of other good examples and practice problems, so I'm going to try to put those in part 2 and finish up alkene nomenclature. Okay. So here we have part 2, and just a little reminder, part 1 was number 03D20. Okay. The last thing we actually did in this video was to look at a molecule where it was very difficult to figure out the size, because cis-trans actually is based on size, and it's useful because normally cis-alkenes, you have those two groups that are going in the same direction bumping into each other, and typically trans-alkenes are the most stable. But in terms of nomenclature, where we want to have very systematic rules, the EZ nomenclature is the way to go. And again, let me draw the example that we use to assign E and Z. Honestly, these four groups on the double bond, and when I say four groups, put dots on the double bond carbons, and you'll see that there are four things attached to them. Now, of course, one of these could have been hydrogen. I normally don't consider hydrogen a group, but it is, you would consider it as a priority, or one of the priorities, because when you assign E and Z, okay, you're looking at the two things attached to each of the dots, and you only consider one dot at a time. And what were our choices? E and Z. Remember, E is opposite, and Z is same side, the same side, or together. Okay. And again, when I talk about priorities, we're using the Kahn-Ingold-Prelog rules that we use for RNS designation. But again, only look at the two things attached to the dot. Don't look at this other carbon. Don't go across the double bond. Just focus on the two groups on pink, which is the NH2 and the I. In terms of prioritizing, I has a high priority because I has a larger atomic number than nitrogen. So that's why it's systematic. We're not looking at the whole group and trying to guess the size. We're doing just like RNS. We look at the atom directly attached to this carbon. This is not a chiral carbon, okay? But again, pretend that you have two stick figures standing here and walk one bond away and figure out who has higher priority. When we do the purple dot is connected to methyl and OH. Again, you don't look at the pink dot. Just look at the purple dot and you only consider what's connected to that, okay, but not the pink dot. These two groups. Oxygen has a higher priority than carbon. This is opposite, so this is E. On Gigan, meaning opposite. Okay. The last thing we did in part 1 was we learned how to make the Z isomer. And you just take either these two groups and switch them, or these two groups and switch them. Okay. Let me go over maybe 2 or 3 other examples with E and Z, and I'm going to show you that it can be a little bit tricky if you're trying to make the other isomer. So whether we have E or Z, let's see if we could name it completely, actually, and then draw the opposite isomer. Because we're not going to name this. There are functional groups here that I haven't taught, or it's very early in the semester to know what they're called. But we should be able to name something like this. I want to keep that hydrogen, and let's make this like that. Okay. You have a choice. Either you could start naming the molecule with all the substituents and the location of the double bond, or you could assign E and Z. I would rather first name the molecule and then assign E and Z to finish up the name. Carbon number 1 is there on the right. Okay, and don't take any shortcuts. Circle your substituents. Make sure you bisect the bond with your dotted line. And this is 2-bromo. I almost said 2-methyl, right? But that CH3 is part of the parent. So 2-bromo 2-hexene. You notice that the 2 represents where the double bond starts. Okay. This molecule does have E and Z designation. Not all alkenes have E and Z, and towards the end of the video we'll take a look at those exceptions. For this one you can assign E and Z. Let's do the 2-dot method again. So I never really spelled this out on the last video. 2-dot method. Pink and purple. Let's do the pink first. Okay. If you think it's too cluttered, then just redraw the molecule and just focus on now E and Z. Okay, get rid of all green writing. Which has higher priority, a bromine or a carbon? Bromine has a higher atomic mass or atomic number than carbon. And this one right here, you got to realize that this, let's use purple. This purple dot is connected to 2 groups, or you can say 1 group and a hydrogen. We should say that actually. I don't want to say hydrogen as a group, but it is an atom that's attached to this purple dot. Therefore, we are comparing this group going up and this hydrogen. Now, don't look at the whole group again. You know, with R and S, you're only comparing atom to atom. So you're comparing a carbon versus a hydrogen, and this is why geometry is important, because you want to know that this hydrogen is going straight down, that the angle made here on paper and in real life is 120 degrees. If you need to draw it, go ahead and draw it. Okay, like that. Now hopefully that makes it very clear that when you draw the higher priority, it is actually going in the same direction as the arrow. Definitely in the same direction in the arrow than the hydrogen. The hydrogen is going down. So this is same side, Z, same side. And you normally put the E and Z notation in parentheses and put a dash. So no spaces, but there's a dash between each number and letter, and in this case parentheses and number. Okay. How do I draw the E? Question mark E. And the rest of the name will be the same. How do I draw E2-bromo 2-hexene? See, this hydrogen is important that you know the geometry, because your molecule is going to look a little bit weird if you don't know it. Because what I'm going to do here is I'm going to keep the right side the same, and the trick to get the other isomer is to switch to 2 groups on one of the dots. So if I switch this propyl group with hydrogen, your hydrogen should look like this, okay? And your propyl group should look like this, straight down, 1, 2, 3. Okay, that will be the E isomer. And you can double check. Let's do the dots again. Pink, bromine wins over carbon. Purple, carbon wins over hydrogen. In terms of semantics, I would say that this double bond has 3 groups on it, a bromine, methyl, and this propyl. But again, when you're assigning E and Z, only compare the 2 groups on the pink dot and then the 2 groups on the purple dot, and draw your arrows. Okay, so that's E. At home, go ahead and try this. Pause the video and do the problem, and when you're done, unpause the video. Okay. I know that this will have easy stereoisomerism. I'm going to show you a trick towards the end of the video, or towards the middle of the video. How do I know quickly whether I could do easy or not? Because there are going to be molecules, alkene molecules that can't do E and Z. But let's set that aside. This is 1, 2, 3, 4, 5. Oh, so interesting. 6. So it's 6 is the longest continuous carbon chain, and the end closest to the double bond could be the left, 1, 2, 3. But man, it could also be the right, 1, 2, 3. I'm not 100% sure. What can I do? I could draw the molecule again and number it a different way, and then compare the two numbering systems. I made this harder than I intended, but no problem. This is still doable. See, we still have a 6-membered parent, 6-carbon parent, numbering from the right. If I take a look at the substituents here, I get our first substituent at 3, then 4, then 6. The methyl, the fluorine, and the bromine. But if I look at this numbering, I get a substituent at 1, 3, and 4. You're going to play your best card first. Oh no, let's not call it that. You're going to compare where the first substituent appears. 3 versus 1. This is the winner. Okay. A little bit tricky, but we have the numbering now. Alphabetize. 1 bromo. Okay, so that comes first, not because it's 1, it's because bromo is first in the alphabet before fluoro and methyl. It just happens to be in order in terms of numbering also. Fluoro. Okay, so make sure that's how you spell it. 4-methyl. The double bond occurs at 3, and there are 6 carbons. Hex. Not hexane, but hexene. Okay. It's kind of cluttered, so I'm going to draw this molecule one last time to assign E and Z. Two dots. Let's do the pink dot on the left. I'm comparing this carbon with this carbon. When you have a tie with R and S, do you remember you play cards? And this person plays HHH. This person plays a carbon and then 2 hydrogens. The higher priority is going that way. I am going fast using the prioritizing rules because these are the same rules that you use with stereochemistry, R and S. If that was a little bit quick, then go ahead and review R and S stereochemistry, or it may be called chirality in your textbook, or stereochemistry. But prioritizing. Here's the purple dot. F beats carbon. I notice that this is same side, Z. A little messy. Z. Now if I wanted E, and I want to make a stereoisomer, and particularly what's called a diastereomer, I can switch these two groups, or I can switch these two groups. Don't switch both. Either switch the 2 groups on the pink, or switch the 2 groups on the purple. If you switch the 2 groups on the pink, and your classmate switches the 2 groups on the purple, you will get exactly the same molecule. And you can prove it to yourself. Just get a classmate and then make models of switching these 2 groups versus switching these 2 groups. Okay. Let us move on. We'll come back to these acyclic alkenes, but I want to quickly go through cyclic alkenes. Alkenes that are part of a ring. Now, there could be many complications. I'm going to do the simple ones here, but this should get most students maybe 90% to 100% of the naming of alkenes. Let me draw this one here. For my class, if I have a ring and a carbon chain, the parent is always going to be the ring. Okay. There are rules to decide there are rules that dictate that sometimes the chain will be the parent, but for me, I'm going to make sure that my molecules follow the rules where the ring is the parent. We still have to follow one of the most important rules in naming alkenes, is that the parent, the double bond, both carbons of the double bond have to be part of the parent. But when we're cyclic, there's another hint or another tip. When cyclic, the parent ring, carbon 1 and carbon 2 are the carbons of the double bonds. Not the best way to say this. What I should have said was the double bond is always carbon 1 and 2 when it's part of a ring. But there are two ways to number it 1 and 2. You could either number it like this, 1 and 2, and this substituent will be a number 5, or if I do 1, 2, like this way, the substituent would be carbon number 4. So this is the winner because the double bond is always on carbon number 1, okay, between 1 and 2, but you consider it starting on carbon number 1. So now we have to go to a tiebreaker, which is a substituent, and we got this substituent at 4, which is better than having it at 5. Okay, that's the winner. The parent is a cyclo, remember cyclo, and it's 6 carbons, so cyclohexene. The substituent is on 4. 4 propyl. Now, it's not ambiguous. You don't have to put, and you shouldn't put 1 cyclohexene, because in a ring, the double bond is automatically carbon 1 for the vast majority of cases. Now, there could be some situations where you have 2 double bonds. I'm not going to go through that. Okay, so if you have 1 double bond in the cyclic molecule, it's always going to be counted as on carbon number 1 and in between carbon 1 and 2. So you don't have to put a 1 here because it's not ambiguous. It's, you know how to draw the molecule. If I say 4-propyl cyclohexene. Cyclo because it's cyclic, hex because it's 6 carbons in the ring, ene because it's a double bond. No 1 there. And there is no example that I can think of very easily where you have to put any number to indicate where the double bond is on a ring. Let me show you this example. Let's have 5 carbon ring, put a double bond here and a chloro here. So we have 2 substituents. Again, the double bond has to be 1, 2. 1, 2, 3, or 1, 2, 3, 4, 5. So let me just finish counting out 5 here. Now this is tricky because if you're looking just at the chlorine substituent, the chloro group, we have a 3 versus a 5. So it looks like the molecule on the left is the winner. And I followed the rule that the carbon double bond is 1 and 2. But do you notice that if I number it this way, this is why I suggest, even if it looks very simple, to circle your substituents. Because actually this methyl group is determining what numbering should take place. Because here I literally get a substituent with this numbering system on 2 and 3. But in this case I get 1 and 5. You may think, well, 2 and 3 is smaller than 1 and 5 when you add them up. Remember, you don't add these up. You compare where the first substituent occurs. And if you have a winner, you stop. You don't go and consider the second substituent. So after the first round, after the first comparison where you're comparing where the first substituent occurs, yeah, 1 beats 2, and actually this numbering is the winner. This molecule is 5-chloro, 1-methyl, and you don't have to say 1-cyclopentene. There's no doubt. It's not ambiguous. So this is cycloalkene. I know that in the previous page of notes we were emphasizing E and Z. For small rings, it's unlikely that, for instance, for this 6-membered ring, it's unlikely that we'll have this bond going to the left. Okay, because then it's not long enough to complete the ring. So I would say that for rings that are 6 carbons or 6 atoms and smaller, don't worry about E and Z. Don't worry about E and Z. So I'm not going to put E and Z in either of these cases. Now, if our ring is a little bit bigger, then we have an opportunity to get these stereoisomers. Go ahead and pause the video to copy that. Actually, let's add 2 double bonds. One here and one here. Okay. Finish copying this. Okay. I'm not going to name the molecule because this is a diene, cyclodiene. What I am concerned about is a possible question or problem in the exam could be assign E and Z. Okay, so you want to use a 2-dot method. Okay, 2-dot method. And here's a pink dot, and here's a purple dot. So we'll do the double bond on the right first. And again, practice with your models because it would be very helpful and you'll understand the geometry and the naming better if you know that this hydrogen is literally to the, I don't know, the 2 o'clock position. Okay, slanted to the northeast. Can you assign E and Z now? Well, one last thing. This hydrogen is right here. Again, we're trying to show trigonal planar geometry. If you make a model, the molecule will look like this. Just flatten it out. The 2 hydrogens will be this way. So when we do prioritizing, on the pink dot, the higher priority is to the left. For the purple dot, the higher priority is on the right, opposite E. If we do E and Z on this double bond on the bottom left, okay, without drawing the hydrogens, okay, we know the higher priority is to that carbon for the pink dot, and for the purple dot, the higher priority is that carbon. That's in the general same direction. Because what would be the opposite? The opposite is if the priority was here. That's where the bond would be for a carbon-carbon double bond. The other group would be here and here. And if you want to draw it, as long as you draw it correctly, the grader shouldn't take any points. You could help yourself by drawing out the hydrogens. Look at that. This is the same side. Z. Okay, so that's E and Z. Okay. Now, if you reviewed the first part, which was video 03D20, the first couple of examples, we didn't assign E and Z. The first couple examples look like this. Okay, so I'm going to draw a couple and then go ahead and copy them. Another example was this, and a third example was this. If you took notes on that previous video, 03D20, our first examples of naming, I believe, were these 3 molecules, and we didn't do E and Z. Why? Remember, this was propene. You don't have to say 1 propene, and you shouldn't say 1 propene. It's automatically carbon number 1 because, well, there is no such thing as 2 propene. And obviously there's no such thing as 3-propene. 1, 2, 3. But no E and Z also. So don't put a 1, because if the double bond was on the left, then 1 would be this carbon. It's unavoidable. But also, there's no E and Z, because look what we get when we do the 2-dot method. Pink, purple. For the purple carbon, we're comparing a hydrogen that goes straight up and a methyl group that goes to the left. So the higher priority is towards the carbon. What about the pink dot? Do you see how we can't assign any priority because they're both hydrogens? When you have a dot that has 2 of the same groups or 2 hydrogens, then you cannot assign E and Z. You can think of it this way. If you really thought this was Z, how do you draw E? Because when I switch these 2 groups, I get the same molecule. So I'm not changing it to a different molecule. I'm not changing it to its stereoisomer or specifically its diastereomer. Look at pink and purple in this case. See that pink dot is connected to 2 methyl groups. There's no E and Z. The way you could say it is there's no E-Z isomerism. Same thing here. No E-Z isomerism. You can't assign E and Z in this case. For this molecule here, purple dot, pink dot. Sure, the pink dot has the priority. The higher priority is to the left of the pink dot. But for the purple dot, we have 2 hydrogens. We can't assign priority for the purple dot. There is no E-Z. I'm checking out my time. Okay. One more problem that I particularly like. It's going to ask you to use E and Z from a different point of view. And the point of view is this. 1 iodo, 1 butene. And another name I'm going to use is 2-methyl, I hope I don't run out of time, 2-pentene. The question is, which of these, if any, have easy isomerism? Because one of these I think does not. So if I draw out 1 iodo, 1 butene, start out with your parent. 1 butene looks like this, and 1 iodo. So do you notice that I could have drawn the iodine like this, or I could have drawn the iodine like that. Again, that's why modeling is important, because I'm not going to go through the 2-dot method. I could tell easily that this is E, opposite, and this is Z. Now look at 2-methyl pentene. Draw your pentene first, and you have the 2 is where the double bond starts, and then on the 2 position, right, this is 1, this is 2. At the 2 position we have another methyl group. So 2-methyl 2-pentene. Do you notice that this has no EZ because this carbon has 2 of the same groups attached to it? Okay. So yeah, go ahead and put the pink and the purple to demonstrate that each of those 2 dots have 2 different groups. And here, my pink dot has 2 methyl groups. Your conclusion here is that there is no EZ. So the problem again, in black, was maybe draw molecule and show EZ if it exists. Just by looking at the name, it's hard to tell whether E and Z can exist. What you would want to do is you want to draw it out and realize that, oh, for one of the dots, for both the dots, we have 2 different groups. Okay. Again, I started out with 1 butene, and when I drew the iodine, I knew I could have either put it here or down, which is in this case a hydrogen. Okay. And if you want to double check, you could always put in the hydrogens and realize that yes, I can assign E and Z.